guys!
It's us, Dora.
And Martin!
And today's video is on
heating and cooling curves!
Let's see now what happens when we add heat to a substance that goes through phase changes. We'll think about 1 gram of water, and let's start with that in ice form at negative 30 degrees Celsius. We need to add some heat to warm that up to 0 degrees Celsius, to add some more heat to melt the ice, no change of temperature there, add some more heat to warm up that liquid water, and add some more heat still to boil that liquid water to vapor. And then, of course, once the water was in vapor form and gaseous form, we could add some more heat there to raise its temperature. So if you're thinking about all this, you can realize, there's actually several different things going on here. And we won't be able to use our Q equal mc delta T expressions across the phase changes. Obviously, one good reason is that delta T is equal to, 0 across a phase change, and yet you still need energy. And that's because heat energy is required to break bonds between neighboring particles, like, for example, the particles that are in solid phase, and break the bonds and loosen them up, allow them to be liquid, or between the liquid particles and drive them apart to become gases. Anyway, let's see about some other way to calculate the energy needed for these phase changes. Remember, Q equal mc delta T is not going to work. Well, the first thing is, think then about the heat that's needed to fuse or melt this water from ice to liquid form. We'll use the heat of fusion and multiply that by the mass. The units will be joules and joules per gram and grams. And for water, it turns out the heat of fusion is 334 joules per gram. It takes 334 joules to melt 1 gram of water ice at 0 Celsius. Okay, and you would also get this energy back if you were to freeze the water into solid form from a liquid form. To vaporize the water, we'll need the heat of vaporization times the mass. In this case, again, the heat of vaporization is quite a bit greater than the heat of fusion. It's 2258 joule per gram to boil that water liquid off to gas, to vaporize it, okay? And of course, you get this energy back if you were to condense gas vapor into liquid. So you have these Q equal HF and Q equal HV, in either case, both times M. So let's look at our diagram again, and we'll just take this off here, and look at these on the bottom here can now be heat. There's Q equal mc delta T to warm the ice. We'll need Q equal HF times M to melt the ice. Q equal mc delta T again, this time C for the liquid water. Q equal HV times M to vaporize that, and then Q equal mc delta T at the end to warm up the water gas. Here are the values. Cp for solid water is 2.108 joule, HF 334 joule per gram. Cp for water in the liquid form, 4.184 joule per gram degrees Celsius. The heat of vaporization is quite a lot, it's 2258 joule per gram. And finally, the heat capacity for water vapor is 1.996 joule per gram degrees Celsius. You got to just think carefully about this for a second. All of these are for water. Other substances, have their own values for these constants, and of course, in each phase. Let's see how we can use all of this. Let's take an example of a person who decides to eat snow as a way to get some water. Perhaps it's cold out and don't have anything to drink and think, I'll just eat some snow. By the way, this is not a good idea, and we'll soon see why it isn't. Anyway, she decides to eat 400 grams of snow, which is currently at negative 22 degrees Celsius. And our question is, how much energy, heat energy anyway, does her body lose in this process? So we'll have to see this as 3 separate components of energy. We'll have to warm the ice up from negative 22 to 0, we'll melt it, and then we'll warm the liquid water from 0 to 37. So the total heat energy required is going to be in 3 pieces. And let's just get those 3 pieces here. So this first one here, the energy to warm up the ice from negative 22 to 0 Celsius, we'll just do that one in the first step. In the second step, we'll get the energy to melt the ice, and then the third step, the energy to warm up the liquid water from 0 degrees Celsius to 37 degrees, which is, of course, the internal body temperature of someone who's not hypothermic. Hopefully our person isn't. So this green component of heat down there, that'll be the energy to warm up the ice, you can see. The yellow one will be the energy needed to melt the ice, no delta T across there. And finally, the blue one will be energy needed to warm up the liquid water. Okay, so let's calculate these 3 different components. The first one, again, for this is the warming up the ice. We'll need Q equal mc delta T for this. Put in the mass of water, the heat capacity for solid water, and also the change in temperature. Minus that 0, negative 0 minus negative 22. So that's plus 22 degrees. Get our calculator here and calculate this. Make sure you do it properly. And you get 18,550 joules. If you were going to report this value, it's just 2 sig figs. Remember, that would be 1.9 by 10 to the 4 joules. Okay, now to melt the ice, we'll need Q equal HF, the heat of fusion, times the mass of water. So it's 334 joule per gram, 400 grams of water, remember. And we'll calculate this one. Get our calculator going, and you get 133,600. This one has 3 significant digits, so that's 1.34 times 10 to the 5 joules. And the last part here, this is the warming up the liquid water. Again, Q equal mc delta T. Make sure you use the correct C value. Notice this is the one for liquid water now. And final mass initial, plus 37 degrees. Let's just calculate here. And that gets you 61923 joules. So this one has 2 sig figs. That'd be 6.2 by 10 to the 4 joules. It's probably a good idea to check the units. So let's be sure that we do that. You know, honestly, we probably should have done this during rather than after calculating. But anyway, that's okay. We'll check now. I think it'll work out. So let's go and have a look. These guys here, they all cancel up. We get joules. Cancel there, get joules. And here at the end, we get joules. So that's good. Everything turns out in joules, and we're all good. All that's left now is to add up the heats. So notice the values. We have them above, and I'll just recollect them down here. The first one was 18,550. Notice that's 2 significant figures. The third one was 13,600. It was 3 significant figures. And the third one is 61,923. So those are the 3 values we got from above. If you add them up, you get this 214,073 joules. Remember, we're adding, so you follow the decimal places and you get 214,000 joules or 214 kilojoules. Remember, mind the decimal places when you're adding. That's a significant figures rule. So now it's clear that eating 400 grams of snow was a very poor idea. Look at all the energy she lost. 214 kilojoules of energy she had to lose to bring that water up to body temperature. If you're out in the cold, try to avoid eating snow. Of course, remember, if we cool a sample, all the calculations are the same, except the delta T values will be negative, and all the phase changes will release rather than require energy. Okay, so let's now summarize. These are the constants we have for water. Just remember, have a look here. You see the HF and HVAP there, the fusion and the vaporization ones, and all the CP values. Just remember, each substance has its own CP, HV, HF values, each substance in each phase. So don't just memorize these water ones. This only work for water. Anyway, that's about it for now about heating and cooling curves. Thanks, and see you soon. Have a look at the next 2 videos in the playlist for more, and stay tuned for our next lesson in Chemistry 11, Lesson 9, Modeling Lab Data.
This is my dad's YouTube channel. It's awesome. So like, comment, and subscribe!
Hey, let's just like...
Yeah, he's still recording.